everybody. I'm Shayda. I will be talking about classification and segmentation of infant sleep from natural overnight and crib sleep videos. And I'm a first-year PhD student at Northeastern University, working under the supervision of Professor Sarah Ostadabbas in the Augmented Cognition Lab. All right, so we can start by asking ourselves, why should we monitor infant sleep? Why is it important? Well, infant sleep plays a vital role in early brain development, cognitive function, and overall well-being of infants. And understanding and learning disruptions in their sleep patterns during infancy can signal developmental issues and have long-term implications for their health and neurodevelopment. And their sleep patterns undergo significant changes in the early months and years of their life, typically transitioning within the first few months of life from an ultradian rhythm with multiple hours-long sleep cycles per day to a circadian rhythm aligned more with the 24-hour cycle. And recent research has demonstrated there's a strong connection between neonatal development and sleep cycle regularity in infants. So this is the motivation we address this problem with. And given we're all, computer vision enthusiasts here, we are really the solution that we focus on is a computer vision-based approach. The problem with existing methods is that they are intrusive, expensive, and uncomfortable, which ultimately limit their widespread use. The gold standard right now for sleep monitoring is something called polysomnography, or PSG. And PSG involves recording physiological signals using multiple contact sensors. This can cause discomfort and disrupt natural sleep cycles. And so it could potentially not capture the natural sleep that we really are aiming to understand and learn from these infants. When they're connected or hooked up to wires and sensors, that could cause that in itself can cause discomfort that cannot allow us to get, those natural a natural understanding. And plus, we want to be able to, deploy these, in an at-home solution, not in hospitals or labs where you're more constrained in your environment. So our solution is to use computer vision techniques to develop a non-invasive, scalable system for infant sleep-wake classification from naturalistic overnight videos. And what do we mean by naturalistic overnight videos is that the data set that we work with here involves overnight videos that were recorded at home. All the infants were sleeping in their crib at home. They, weren't brought into a different house, weren't brought into a lab, weren't recorded in the hospital. And a lot of existing computer vision solutions that focus on understanding infant sleep are generally found in, generally the data sets that they use are either from NICU environments or hospital environments where, you have more, controllable factors rather than, being in the comfort of your own home. So it brings a challenge that we like to address. So towards a computer vision-based approach. So the goal here for the first half of my presentation was to take a 90-second clip that was sampled from these overnight videos of infants. And the videos range from anywhere from 6 to 10 hours, depending on how long the infant slept that night. And the goal would be to classify whether the infant is asleep or awake just from this 90-second video clip that is drawn from this longer baby monitor footage. And so our contributions include the small sleeps data set that we created, which was an annotated data set where the ground truth of the sleep and the wake states were given by two annotators. And actually going on into the next phase of this project, we have actually two more annotators that went through all these videos and labeled whether the infant was asleep or awake during each time period. And using that data set and creating those, just sampling 90-second clips from those footage, we were able to develop a novel spatiotemporal network that classifies the sleep and wake states from those from the video footage. And again, the data set includes over 152 hours of overnight recordings, recorded at 10 frames per second of 17 different infants in 17 different households aged 4 to 11 months. And behavioral coding was employed to annotate the sleep and the wake states, which allows for the non-invasive data collection rather than, with a PSG-based approach. Rather, this is just annotated by annotators visually looking at the video and understanding whether the infant is asleep or awake. So the reason for sampling these short video clips began with first trying to understand this problem as a classification problem and trying to just classify those 90-second clips. But our longer term goal is to develop a model capable of classifying and temporally segmenting the sleep-wake states in longer naturalistic overnight recordings. So potentially looking at the full 8-hour fridge and be able to segment when the infant, is asleep, wake, and segment the video in that manner. But the first step in doing that was to just understand what are maybe the most important features in just understanding and classifying sleep and wake states from these videos. So that is where we began here in this paper and in this work. And for the creation of the training and the test set, we had 17 different infants overall, and we used 10 subjects, 10 of the infants for training and 7 for testing. And this allows us to get a realistic test of the model's ability to generalize to new environments and different conditions. And we introduced this idea of pure state versus mixed state clips to be able to understand the transitions and how the model will learn to classify when you're kind of in between certain states. And this came with the motivation of being able to, when you want to look at this from rather than a segmentation, rather than a classification approach, when you want to shift into a segmentation solution, we need to understand those boundary cases when you're just going into the wake state or just coming out of the wake state and going into the sleep state. So we introduced these idea of bins, which kind of capture the percentage of time it is in the labeled state. So the model can potentially learn to identify those transition periods that could be informative for the segmentation problem later on. So the proposed method for the classification, we have this end-to-end sleep-wake classifier, which comprises of a two-stream architecture that combines both RGB frames for spatial information and optical flow for the motion dynamics. We use the inflated 3D convolutor i3D as the backbone for our feature extraction, and this really stems, we decided to use this approach because it is shown to be very good in capturing the spatiotemporal patterns in the video data. And it's well suited for the spatiotemporal feature extraction because it extends the 2D CNN filters into the temporal dimension, enabling better motion representation throughout the 90-second clip. And it allows us to integrate both the spatial RGB features as well as the optical flow features into our model for classification. So the input is the 90-second video clip from one of the 3 bins. It samples keyframes uniformly across the temporal dimension and extracts both RGB information and uses RAF to capture optical flow information. Then the i3D model processes these inputs through a series of 3D convolutions that allow us to maintain temporal information while also learning the informative spatial features. That's happening in the green box here. And then those extracted features from each stream are then each independently processed through a temporal self-attention module to capture these longer range dependencies between both the RGB and flow features across the time dimension. And then the 2 streams of information are then fused and passed through a final classification layer to output the sleep and wake probabilities for this clip. So just briefly go through our results here. We looked at several different models to understand what is the most informative feature in truly capturing the sleep and wake states. And so when just using RGB features alone, our models achieved moderate accuracy of 72 and 71%, and the 2 different values correspond to the data sets that it was trained on. So at the top one, it was just trained on clips that were in the 90 to 100 band, which represents the percentage of time the 90-second clip was in the labeled state. And this one includes more of the mixed state clips into the training. Notably, though, when we introduce optical flow features in addition to the RGB, capturing the spatiotemporal aspect of the clips, this results in a substantial improvement in our model performance, which you can see from the green boxes in this idea of when we capture the RGB and the flow features in our classifier. So these results really showed us the importance of optical flow in capturing the subtle wake events, particularly in the mixed state clips. And these optical flow features, we learned that enables the model to more effectively differentiate between the sleep and wake rather than just the RGB features alone. And this is captured in when we did a TSNE plot of the RGB features and the optical flow features. You can notice in the top, and maybe hard to see a bit, but the open circle represents the sleep class and the closed X represents the wake class. And the different colors are the 7 different validation subjects that we had. So in the RGB features, when we plotted, we can see that there are clusterings for each infant, right? You see a division between the colors, but not so much of a clear division between the sleep and the wake states, which is what we want to be able to discriminate. However, in the optical flow features, you can see a very, clear divide between the sleep states and the wake states. So you can see that these distinct clusters for the wake states that we observe indicate that those motion patterns provide a unique signature for each subject during the wake states and allow us to discriminate between understand when the infant transitions in and out of that state more effectively than just RGB features alone. So from this work, we were able to develop this spatiotemporal deep learning model for sleep-wake classifications trained on our own annotated real-world overnight infant sleep data set. And this moves us towards creates a non-invasive scalable solution for infant sleep monitoring that bridges the gap between research and real-world applications. However, I mentioned earlier that we want to move beyond just the classification horizon and develop a model ultimately capable of classifying and temporally segmenting these longer overnight recordings. So rather than just sampling, the 90-second clips, what if we had a 20-minute, 30-minute, or even hours-long footage that we want to temporally segment based on the different states, in this case, sleep and wake, that the infant can move in and out of overnight. So we then come into this with a new perspective. What can we learn about transitioning between sleep and wake states for longer full video segmentation on the edge? So, we have our sleep state and our wake state in this case, but this can really generalize to, a much larger space of actions that, humans are capable of. If, I'm sitting here, then I want to pick up my phone and then read, but if I continue this for an hour, how can I learn to temporally segment this through a longer video rather than just a few minutes or 30 seconds, say. So this is where we are shifting and currently researching this idea of using hidden Markov models for video segmentation. And you can see here now I'm focusing on a longer range clip, perhaps a 20-minute sampled video segment, where we can define smaller action primitives where the model extracts features from those action primitives and those features serves as the observed data that the model can then learn to identify the most probable state that the infant will be in given those features. So why an HMM? So I'm sure that you noticed that compared to, previously presented algorithms, this is a much more, basic building blocks. Kind of the field of video segmentation kind of started in this idea of using hidden Markov models. But truly, I think we start here and we start the solution for video segmentation here because of the fact that we wanted to keep the complexity of our models low enough to handle the amount of data that we have available, right? There aren't large and massive data sets of infants overnight sleep that we can use and, pass through a much larger model and learn a bunch of features from, but rather if we, keep it simple, given the data set size that we have, what is the, most simple, maybe simple is the wrong word here, but the best solution that can handle the amount of data that we have, which is not much in this case. So this is why the problem of sleep-wake segmentation can be formulated as a sequential classification task, or using a hidden Markov model where the hidden state in our HMM is at each time step represents whether the infant is asleep or awake, and the observations of the observed data here is extracted from RGB video features, such as in this case we look at maybe the pose and the optical flow, but this can be any features that we think are most telling in identifying these in this case the specific sleep or wake states. So then the task of this segmentation becomes to estimate the most probable sequence or the most probable hidden state sequence over the entire video or over the entire, let's say 20-minute video in this case, using the HMM framework and the posterior probability of the hidden states is expressed. And learning, in this case, we're doing a neural network HMM, which basically just means from the features we use a neural emission model to learn the emission probabilities. And so, yeah, so this represents this idea of shifting just from a classification to be able to segment longer videos. And so in this case, one approach that we're looking at now is to look at the pose and the optical flow as a set of observed features that to which we can decide what is the most probable state we're in given the set of features, and then use the Viterbi algorithm to backtrack and set and label our entire sequence, our entire overnight video sequence of the states that we could potentially, the most probable sequence of states we can be in. And here I also present some, videos, and the bar at the bottom represents the ground truth of being in the sleep or wake, where blue is in the sleep state and red is the ground truth of wake. But this will give us, and these actually each are, they're fully 20-minute clips, but they're condensed, or I guess summarized to capture 2 frames for every minute of the video to kind of summarize information and try to see what is the least amount of information that captures the least amount of frames that captures the most information for us to, observe these features from. So this is a current area of research, and we're still, working on ultimately finding the best solution, understanding what are the best features that allow us to segment these overnight videos. And this may involve incorporating perhaps more fine-tuned facial cues to capture maybe certain eye movements, maybe even respiration, or rather than just looking at pose, which may be more challenging, when the infant is bundled around a blanket, maybe using point trackers to cover the entire infant's body and capturing the movement in that way. But ultimately, we want to adapt this system for real-world deployment on the edge that supports both researchers and parents and sleep health monitoring. So this is the end of my talk. I'm not sure if there are any questions.
Yeah, there's 3 questions, and why don't we take the first one? The first one came during your results performance comparison, optical flow and RGB features slide, and the question is, what is optical flow and its features? I think you kind of covered some of that, but maybe a quick double click on that.
Yeah, so the optical flow here will represent, I guess, the flow in the initial classification in the initial model, we look at the flow between the entire frame over, let's say if we're looking at the 90-second clip and we sample, I don't know, 100 frames from it, the optical flow looks at, I guess, the motion between each frame. So pixel by pixel motion between each frame. And rather than you can capture like all the motion dynamics throughout the video. So if there's the infant is moving around, that will be captured by the optical flow throughout the entire clip. But compared to the RGB features, that just looks at the spatial information within the frame. This can also go back to when we looked at the TSNE plot of the different clustering. The RGB features really captured each infant's specific, I guess, spatial features, because if they're wearing a certain clothing, it's going to kind of look the same for one infant over all their video clips, but it's going to be different for each. That's why you kind of saw infant by infant clustering rather than by the different state. But the optical flow doesn't really care about what the infant's wearing or not, but rather looks at the motion dynamics throughout the entire clip.
And
so
our next question, go ahead.
Yeah, go ahead.
I was going to say that our next question came during the sample video slide, which was towards the very end. Is it possible to segment sleep phases like REM, deep and shallow sleep, probably using the gold standard ground truth instead of by looking and manually segmenting the videos?
I guess to capture sleep stages, that is an exciting area to move towards. I guess the next the next step after sleep wake would be, capturing the different stages of sleep. But I guess with the ground truth that we have right now, which is the sleep versus the wake, we can't capture that because we don't have, the ground truth of the, if it's an REM or not. But I think that would be an exciting area to move towards after kind of solving just the sleep and the wake. Yeah.
And we'll take two last questions. The next one is your features are all error prone. How do you make sure the errors are not from your features rather than your classification model?
Yeah, I guess I mean I don't have an exact answer for that. I mean, we're still learning and understanding what could be the most, I guess, good features. I guess that comes with more research and understanding, looking through the videos, but I don't have an exact answer. Yes, they can be error prone, but we're still trying to learn what the best set of features could be, or perhaps learning what the best set of features could be for this problem.
Cool. And we'll take one last question, which seems to be a popular question these days, is can you give some color or background in regards to the resources that were required, GPU, et cetera, things like that?
Yeah, so for this, I mean, the classifier didn't require any resources because after we extracted the features, it was just a simple classifier. But the resources we used to extract the features, using the i3D model, we just used I think I used a V100 GPU for that, and that just took some time to get through, process all the data set of videos. But the classifier itself, once we had the features, didn't require much compute at all.